Okay, we're going to begin our adventure into physics by first looking at some mathematical concepts which are going to be essential for enabling us to be able to describe the world that we live in. So we're going to be looking at something called vectors and something called scalars. Here's your first definition. A scalar is something that can be defined by a single number. It's something that can be characterized by an amount or quantity. And so here are a few examples of things that would be called scalars. The number of pears in a sack. If I go to the grocery store to buy a bunch of pears for my absolutely delicious pear apple cobbler, I would maybe put 7 or 8 pears in my bag, take them to check out. How many pears are in my bag? 7. There's 7 pears. That's a single number. That's a scalar quantity because it's something that can be characterized by a single number. The average temperature of a room. So, if it's 70 degrees in here on average, that's a single number. It's what defines the average temperature of a room. The length of a piece of string. How long is it? I can get my ruler out. I can measure it. It's 12 centimeters or whatever it is. That is a single number. The volume of water contained in a flask. There's so many things that can be characterized by a single number, and those things are called scalars. It's kind of a funny name, scalar, but we'll see maybe why they call it that in a little bit. Now, another thing that we want to look at is something called a vector. Some things in our universe require more than a single number in order to fully characterize them, and vectors are a perfect example of that. Now, there are many different things that are vectors, but we're going to begin by looking at a very simple one that's easy to understand. The idea of a force. You're going to push on something, you're going to pull on something, you're applying a force to it. Force, it turns out, is an example of a vector. Now, what do I mean that you need more than a single number to fully characterize it? Well, let's look at an example here. We have a crate that's resting on the floor, and from our point of view here, we're kind of looking down, top down onto the crate, and someone's pushing the crate from the side. So we have this force here, this 10 pounds of force is being applied to the crate. And so what's going to happen to the crate? It's going to slide. It's going to slide off to the right. But if I take that same 10 pounds of force and apply it from a different direction, the crate is going to slide in a different direction. It'll slide in the direction that the force is being applied. So each of these cases, I'm pushing on this crate with 10 pounds of force. That's my single number, but I get two very different results. And the reason for that, when you're talking about vector quantities, the direction is important. The direction matters. So just to summarize, we've got two definitions here. We've got our scalar, which is something that can be characterized only by having an amount, something that can be characterized with a single number. And then in the previous slide, we considered two forces of 10 pounds, one pushing to the right, one pushing up, and we saw that there were different results. So we see that there are these things that we call vectors where the direction matters. So what happens if I take my two 10-pound forces and apply them simultaneously? So I've got one force that's pushing to the right, I've got one force that's pushing up. Well, I think you would probably guess, and guess correctly, that if you applied these two forces at the same time, the box would go off diagonally in some direction. It would slide diagonally. I'm adding these two vectors, this vector and that vector, I'm adding them together simultaneously, and what I'm actually doing is a process that we're going to call vector addition. And so we want to know what's the result of our vector addition. This green arrow here represents the direction that it would slide off, and you might guess that in this case where both of these are 10 pounds, it would probably slide off at a 45-degree angle, and you would be right about that. But when we talk about vector addition, what we really mean is what's the equivalent force? So how much force is this green arrow representing? Would it be 20 pounds? Would it be 10 pounds? Would it be something in the middle? That's what we want to be able to figure out. In other words, if I could take these two 10-pound forces and do away with them and replace them with a single rope pulling at this angle, how much force would I have to apply to get the same motion that these two individual 10-pound forces working together would create? That's the equivalent vector. So this vector plus this vector equals that vector. And that's what we want to be able to figure out how to do. How do we get a number that goes with that? Now, in order to do that, we have to really understand what the definition of a vector is. And so I'm going to give you the official definition of a vector in this slide. A vector is an object that is characterized by three things. The first thing, it has a magnitude. That's the amount. A 10-pound force, a 50-pound force, whatever the amount of your vector is, that is its magnitude. But it also has a direction, and there are many ways that we might define a direction. We could say that the force is pushing to the east, or it's pushing along the x-axis, or at a 45-degree angle to the x-axis. We'll see lots of different ways we can define directions, but the key thing is a vector is something that has a magnitude and it has a direction. Now I'll tell you something, it's a little bit of a pet peeve of mine. Most introductory physics books, that's the definition they give for a vector. They say it has a magnitude and a direction. That definition is actually incomplete. Most introductory physics books are actually wrong on this point because it's very important to have this third part of the definition. It obeys the rules of vector addition. Now, we haven't figured out what those rules are yet, but we're going to. And once we know what they are, once we know how vectors add together, that is crucially part of the definition of vector. So we're going to see examples of things later on that have both magnitude and direction, but aren't vectors. So that means that that definition has a magnitude, has a direction. That's not sufficient. But if something has all three of these, if it has a magnitude like a vector, if it has a direction like a vector, and if it adds together like vectors add together, then you can say that puppy is a vector. I just want to take a moment. I want to really harp about how important it is to know the definitions of things. In order to learn physics, it is essential, and notice I've got essential in all caps here because that's important, that you really, and not only is it in all caps, really is made highlighted in red, it is really important that you really learn the definitions of things. We're going to see many different definitions over the course of this semester, and often these definitions are going to be similar to each other, but subtly different in their meaning. And sometimes you can use two words interchangeably and you can get away with it, but sometimes if you use a word that's similar, you're wrong because you don't understand how they're different. And that can lead to misunderstanding, it can lead to an inability to solve problems, and really it means that you haven't learned what you're supposed to learn. So right now we have two definitions. We've got scalar is defined, we've got vector is defined. It's really important that you learn these definitions. I also want to take a quick aside here and talk about how we notate vectors, that is, how we write them down in equations. Scalars, things that are characterized only by a magnitude, they're generally written just normal letters. Vectors, when you have an equation and something in the equation is a vector, usually you'll see it written with a little arrow on top, and that tells you that what you're talking about is a vector. Now, sometimes not all typefaces have that arrow available to them, so you'll see a lot of textbooks, especially older physics textbooks, since they couldn't make the little arrow on top, they make vectors be bold-faced. And so if you see an equation and something is bold-faced, and you have things that are not bold-faced, the things that are not bold-faced are the scalars, the things that are bold-faced probably are the vectors. Okay, so sometimes when we're talking about a vector, we know that a vector does have an amount and it does have a direction. Sometimes the direction is not as important and we want to talk about what the magnitude of the vector is, just how much it is. And we can represent that in an equation with absolute value bars. And so if you see a vector that has absolute value bars written around it, that means that you're talking about just the magnitude of that vector, not its direction. The direction doesn't matter at that moment, but the magnitude is what you want to talk about. And I want to note here, my slide's a little messed up and I'm not going to bother fixing it because I'm almost done with this video and I just noticed it, but magnitudes, one of the reasons why we write them with absolute value bars, they're always positive. Magnitudes are always positive. And so we're going to talk about when you have vectors with minus signs, that minus sign is always going to tell you about the direction, not about the magnitude. And so whenever you want the magnitude of a vector, it's always going to be a positive number. And that's worth noting. So this is what I wanted to cover in this little presentation, and we're going to go on to the next one and learn lots more about vectors than you ever wanted to know.